So I promised you I would talk about the future as well. This future has it's based in reality, which is always good. But I wanted to give you a sense of where this work is going next. So as I said before in the first couple of lectures, there's a bunch of really interesting academic work that's going on in places like OCaml Labs, my research group with my collaborators. And also there's a bunch of industrial activity happening as well with the adoption of Mirage OS. So what we've been trying to do is to guide the development of some of these technologies, but also obviously to stamp our vision of the future, to figure out what we want to happen next. So I'm going to try to give you a combination of these things as well. And along the way, I will drop back into some bits of technology and then take you through how this new generation of programming techniques can help us with scaling to some of the crazy heights that we need to get to. Good news is I found a little embedded device. It was stuck in my coat, so I can pass that around as well. So you can give that a try. So before we start, where do you think the trillion devices are going to come from? We had millions of desktops, billions of virtual machines running in the cloud. Trillions are going to come from all around us. They're going to come from the set of processors that run in our actual physical environment. So that we can have many, many computers in the data center. We can have many, many computers like laptops. But around us, just in permeating our environments, are trillions of microcontrollers and increasingly much more powerful general purpose chips that control things like lighting and heating and pacemakers and smart shoes. And I have a weight scale that tweets my weight. So these so-called Internet of Things are propagating throughout the world at the moment. And as computer scientists, we have a huge challenge in trying to figure out how to scale these things to give them the same levels of robustness and reliability that we have in conventional systems that are growing perhaps less fast. How many of you have tried one of these smart lights out in your house, these overly expensive Hue lights? So, a few of you. So I changed my whole house to Hue lights, and I can turn the light on about 80% of the time now. And my light switch, which is previously a physical circuit, has been replaced with an extraordinarily complicated wireless infrastructure that when you press it, goes off somewhere very far, far away and occasionally turns the lights on after waiting for a different amount of time. So I'm personally motivated to fix my house, and this talk is the beginning of how to do that. Now, one of the biggest problems in the Internet of Things around us is security. So whenever you're in these data centers or if you're on your desktop, your software updates very, very frequently, right? So, and in fact, we've got this culture now where instead of having to manually update, many of your bits of software automatically behind the scenes just update themselves without you even noticing. So this means that a lot of the pieces quite often have big security problems, but you don't notice because Chrome, for example, micro-updates. It's perpetually refreshing itself and almost every day adding in new versions. And so before you even know that there's a problem, it's been auto-updated and it's been patched, and then you can just wait patiently for the next problem to show up. With embedded devices, it's a bit different, right? These things just do not see the same frequency of updates, mainly because they're not connected as much to the outside world. So if we look at this was from an NSDI 2013 paper. We just listed what are known as CVEs, and CVEs are the Center for Vulnerability Exposure in the United States. And what they do is they simply assign a number to track vulnerabilities that are of threat to cyber physical infrastructure. So you can search in this vulnerability database, and you can start to categorize the classes of bugs that you have as well across multiple components that are internet connected. So what we did was we looked at which of these bugs in quite low-level pieces of code would affect, for example, an application. Which of them would allow you to have remote execution? So just by having the bug in your system, you could execute code on the device. Then can you do not service it? Does it expose data? So because it's not so bad that you can execute code, but if you can see all of your data, then I don't need to execute code anyway. And finally, the one Jitsu was a system we built for ARM devices, and we wanted to see if it was vulnerable to these as well, using a lot of the technologies in Mirage OS and so on. So as you can see, a huge number of the bugs are clustered around application-level overflows, and these are all to do with low-level buffer overflows, things to do with how you program your software, using C, for example, and having kind of poor management of memory. And then as we get down the stack, we have embedded systems up here with applications, and these are all protocols that are implemented in Mirage OS now, so these Jitsu-based stacks are completely immune. Then you have Linux, the Linux kernel, and then these start to get much more based on denial of services and exposure of data. So for example, from your wireless devices, if a bug in your device driver happens, then you can see all of the Wi-Fi traffic, no matter how much it's encrypted. You can bypass things like net filters, emulation layers inside the kernel, things like IP fragmentation. And then you're getting to the lowest level, the Zen hypervisor, the bastion of security, the thing that's meant to be small and secure. And it too is having lots and lots of these kind of attacks. And we can't yet build completely verifiable systems that are completely immune to these attacks. So our fundamental thing is, how can we improve the state of the world so that we can get away from these really annoying kind of low-level attacks we've been having for many, many years and try to focus our attention on a smaller trusted computing base, like the Zens or the KVMs or the library hypervisors, where they're still written in C, but their code is relatively immune to execution. So you can't, if you break one of these things, you'll expose data, but you will not be able to run your own code. And this is part of the essence of trying to fix the Internet of Things, because imagine a future where there are no walls, there's no transparency, there's no secrets. Everything is exposed from social networking all the way out. There's a reasonable chance in the next 10 years that there'll be such a serious cyber-physical attack that all of the data in social networking sites will just be exposed by virtue of us not having time to fix it. Hands up, who's heard of Maelstrom and Spectre? About half of you. It got coverage in the New York Times. A single bug in chips that's been lasting for 20 years got coverage in the New York Times because there's just a misunderstanding between what the hardware should do and what the software should do that has led to fundamentally having to re-architect the Linux kernel, the Windows kernel, in order to protect against modern branch predicting software. And this is an incredible place that we're in right now, because in order to do this, the Linux kernel has had to apply many of these page table patches in order to protect itself that has caused a slowdown of something like from something like 1 to 40% on some applications. And if those had been unikernels, it would have been much, much easier to have reorganized the software. But because we're operating in this kind of framework where we have no flexibility in how we run our operating systems, the operating systems have been forced to apply some serious heavyweight mitigations against these bugs. And the rate of these bugs is only increasing. Meltdown and Spectre are remarkable because they happened in something as well established as an x86 chip. But you can imagine things lurking that are far, far worse and will have big exposure. So we're not trying to build a perfect system. We're trying to focus our efforts on the hardware and the lower parts of the software so we can just get away from the kind of high-level bugs. So you've got something like unikernels, and no one's really listening or paying attention. How do you get the world to pay attention to how much better our security is? Because we're claiming here that we're immune to all these kind of attacks. So if you want to get attention in the modern world, what is the buzzword of choice? Blockchain. Hey, well, we did blockchain before it was cool. So what we built was something called the Bitcoin Pinata. And this is about 4 or 5 years ago now, back when Bitcoin was not worth very much. And the idea was very simple. We built a unikernel that held inside itself the secret address for Bitcoin for 10 Bitcoins. They were donated by a donor to the Mirage project. And the intention was not that we spend it. You couldn't spend it on much but pizza back then. But we would publicly construct a pinata, so a unikernel that would actively try to help you to take the Bitcoin. But the only way to get the private keys is by hacking it. So it would cooperate, it would tell you the protocols, it would show you the key exchange mechanisms, there's full instructions how to interact with the Pinata. In fact, the Pinata is still running. And it got to the front page of Hacker News and stuff, and all of those kind of social networking sites. There's millions of attacks against it. The machine kept crashing because people did not have servicing it. But like any good Pinata, people just kept hitting it, just kept bouncing back up, rebooting, going, what's going on? And then 10 milliseconds later, the service is back. Everything's like rebooted thousands of times as it came under attack. It's 2017. We looked inside the Pinata, and it's worth about $180,000 now, because that's what Bitcoin's worth. Hasn't been broken yet because it's in the blockchain. You can't deny when it's been traded. Let me just check, just to make sure I'm telling the truth. If you click in this, if I have the Bitcoin Pinata, so I think I didn't quite make it clickable in my slides. Oh, I did make it clickable. There we go. And so if we try to navigate to the private key, we can see the Bitcoins. And what we see is there's been 8 transactions all going in. So people donated money into the Pinata, but they never actually, no one has taken money out of the Pinata. And this is in 2015. So it's actually a good way to make money as well. Just put a Pinata out there. What have we learned from this exercise? You can never prove the security of something, but you can certainly build confidence in the end-to-end security of a system by doing this kind of thing. And what it taught us was a few important things. We got lots and lots of traces of traffic by building this Pinata, because by putting it out there and letting the world just come and attack you, and being unable to deny if you have genuinely been cracked, because the blockchain will tell the world whenever someone trades this stuff. I think to fund Mirage OS, we're taking a few of the Bitcoins out next week, but we're going to post in the Pinata that it's in fact us, although we are having trouble taking it out ourselves. Hannes Menhert and David Caliper put this together. But what they also did was they took a lot of machine traces and they classified the kind of attacks coming in against us. So you can start to get a sense of how to build systems as more of an immune system. So you can figure out how to defend against big attacks. But the other thing it did as well was to change the way that we're thinking about services, because you can build services that last for a while. We're very, very used to, with our constantly internet-connected systems, of thinking if I don't software update, I'm basically going to get owned and get cracked. But if you build principled, specialized services the way you can with Mirage OS, then you can leave stuff running for some time, for years perhaps. And so you start to think about cyber-physical systems a bit like if you engineer a bridge very, very well, you put in lots of protections and stuff, the bridge might still collapse, but you can start to build confidence in the system, mainly because you know about some of the pieces that went into it as well. And so this is where our thinking about taking Mirage to the Internet of Things came about, because in many ways, it's the perfect technology if you want to bring security and a bit more of a principled programming approach to the Internet of Things. Now, security issues are often the result of just terrible software engineering and just basic problems with buffer overflows. But the real problem in IoT comes from the fact that why are people so careless and why is it so hard to update these systems all the time? Because people write bad code everywhere, right? It's not just IoT. But IoT seems to really concentrate the bad code into your smart heart pacemaker or whatever it is. And that's exactly where you don't want the bad code to be. I'd prefer to have the bad code in my Facebook or whatever. There's websites that are not controlling my immediate physical well-being. And the problem is because there's so much kind of bespoke hardware out there, there's sensors to the outside world. They tend to be very cost sensitive because an extra cent will cost a lot of money. They tend to have very, very custom build systems, firmware that's very hard to use. So even the Raspberry Pi, how many people have a Raspberry Pi here? Tons of you. The Raspberry Pi is a tremendously complicated boot system. It hops across the GPU and then it boots. And so even something as open as the Raspberry Pi is very, very complicated at the lowest levels of booting up. The community has done a great job of opening that up. So one of the challenges, how do we take all of these different IoT devices, not just the Raspberry Pi, and get the same kind of community and ease of use as the Raspberry Pi has today, but for the world's trillion devices? And the other problem is that they all have different ways of connecting, right? So if you know how many times you've lost your Raspberry Pi USB to serial connector, blah, 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 there's just so many of these little connections. There's bespoke wireless as well. And so somehow you have to figure out across all these things, how do you just get software updates rolling to these things, even though they're turned off for 6 months at a time? So as soon as they turn back on, they need to have the latest kind of firmware and stuff given to them. And because they're all about low energy or energy conservation, they don't often use the standard networking protocols. There's many, many different things like Zigbee and Bluetooth, as opposed to the bigger kind of 802.11 Wi-Fi that you're used to. So all these things diverge from the norm. But by and large, though, building an IoT system, apart from this requirement to customize some of the hardware, the software to the hardware, it starts to look very much like a cloud system because you basically want a hardware spec, you want some configuration, and you want to tailor your code to that. So it really looks like a unikernel-shaped problem. Some of these devices look very, very shiny these days. It's worth just realizing the diversity of connectivity because it's not just the form factor, it's where they're used as well. So the Nest devices, for example, they need very low latency reactivity when you're interacting with them, but most of the time they're doing nothing. Weight scales, they actually need to be quite accurate. Little printer is a now defunct but charming way to send messages by printing to a thermal printer. And you have tons of these kind of Fitbits and stuff that are increasingly kind of giving you lifestyle decision-making processes. In fact, one of them, the Nokia weight scale, just got withdrawn from use because it was making estimates about pulse wave velocity. So a metric that tells you a lot about your life expectancy. And so it moved beyond just a lifestyle gadget to tell you your weight to something that actually had to be medically regulated. So the lines are blurring here. And you're seeing just tons of these kind of devices, like sex toys that are internet connected and being owned by these hackers. So really private data is being kind of moved into this domain. So it's really, really important that we provide a good systems approach to building these things. And then it's not just the actual hardware itself. The environments that you're targeting from a language perspective are really, really different. So we had a question earlier about which architectures OCaml supports, and I said it supports a lot. But there's many, many different kind of variations in the layouts of the hardware. So when we use data center hardware, there is a lot of variety, but it's generally been standardized around certain ways to lay out your motherboards and so on, so that operating systems can have a reasonable chance of using PCI to do discovery of devices and so on. In IoT, it's completely different. There's many, many CPUs. For example, the CPUs are ARM, for example, and the CPUs themselves are highly customizable. So whenever you take an ARM, you don't just buy an off-the-shelf ARM processor. ARM license intellectual property to CPU makers, who then take the bits of instructions they want, and they build a perfect instruction set and perfect board for them. So you can do everything from tiny 16-bit instructions like ARM thumb, all the way up to quite big kind of vector processing things. And then there's many different variations. There's MIPS and PowerPC, for example. And now, excitingly, there's even RISC-V, which is an open source hardware spec, the first usable open source hardware description. So in the future, we're starting to already get some boards running real RISC-V hardware, but you can also inspect the underlying program that made the actual CPU, so your open source can continue all the way down. So this is where there's hope for verification and a peer review of all of these pieces. And when it comes to memory, remember I told you about the process models inside these systems, where the actual operating system says that you should have an address space per process, and the CPU will help you protect against those. Well, when you get to the embedded space, all of this work is done by something called the MMU, the memory management unit inside the CPU. And they simply do not have that. So in embedded devices, it's normally quite common to run in a single address space, just like we did with unikernels. They just don't have the hardware protection to manage multiple address spaces. And this means that a normal Linux-style bit of code simply will not work there. And if you're writing IoT code, you then have to write specialist code from embedded devices to run on there. You can't use any of the large kind of bodies of code that we have in the rest of our world. But with unikernels, remember, we've written our code in such a way that we can target different kind of address spaces and models by picking the right abstractions. So we can start to reuse code that we've built for the cloud, for Docker, for Mac, for all of those kind of weird environments, and run them straight on tiny little embedded IoT devices as well. So the flexibility in IoT maps almost directly to the flexibility that we have from our unikernel approach. And power is by far the dominating factor. So at this point in the day, some of your laptops have been all, for all of these lectures, you're going to start running out of power. And when it comes to IoT devices, every cycle counts, because all they're doing is typically something quite simple. They're just sampling a little bit of industrial automation or something. You've got the brakes in a car with its own chips, just looking for pressure reaction and having to react. And these things, they form big distributed systems, but each device is generally doing something quite targeted. So you want to make sure that the systems you build are so optimized that they'll not abuse the fact that the hardware has been designed to be as low power as possible, but then we run 25 million lines of software on it that just takes up all the power. That's kind of a pointless thing. You want the system to be as efficient as possible, and this means looking at the hardware and the software together and optimizing as much as you can. And this is where unikernels shine as well. Environments get even crazier than just little pacemakers and tweeting weight scales. You can go to space. So whenever you're building these environments, if you want to run satellites in space, well, a SpaceX spin-out called Vector a few years ago decided that they wanted more efficiency in the software running in satellites as well. And so whenever you're trying to run in a satellite, you want all the benefits. You want to have virtual machines and Docker containers. Just because you're in space doesn't mean you don't want to run the same software you run on Earth. You might just want to do something with a bit more reliability. And the CPUs in space, for example, are radiation hardened. So if any one cosmic burst comes to one CPU, it can just cause bit flips. And so typically they're built with multiple CPUs acting in tandem, and they're all voting at the same time synchronously in order to make sure that they're all doing the right thing. So again, you want to take the best of breed software from Earth and apply it to space. You don't want to have a very expensive industry that is doing things in a bespoke way, because no matter how good they are, they're never going to beat the network effect of having millions and millions of developers writing and contributing code into one place. So even if you take some of the best programmers, the numbers just don't add up. You want to join the crowd and try to build up a good solid code base that's reusable across multiple contexts. So the environments really go all the way into things like radiation hardening and CPUs. How do you build these systems in such a way that without predicting what hardware we have in the future, we can still build our systems in such a way that we can extend them in the future to work with those rather than rewriting everything? So this is a big challenge. And the library OS approach, as I alluded to, is perfect for the Internet of Things, because it takes this artisanal approach that we've been taking so far for the cloud, but it solves directly all the weaknesses that are inherent in IoT. And I'm normally quite an optimistic person, but IoT is in desperate need of help, because the rate at which these projects are propagating through the world is being outpaced by the rate at which we're fixing our software infrastructure to make them work correctly. So we have to act fast. And what it lets us do is that it lets us look at security holistically, because we can say that we can have type-safe infrastructure where possible. We can build in modern languages like Rust and OCaml that are designed for this infrastructure. But also by using our unikernel style of combining the knowledge of the configuration, the application, and the hardware, we can tailor each of the bits of firmware very, very precisely without modifying the whole system. And also, I showed you the fact that the binaries that result from these things are very small, if your application is reasonably small, and they're perfect for version control. So you can adopt this philosophy of version controlling your entire infrastructure. I'd love to be able to git pull the software in my house, because if it fails, I can git revert back and hopefully get back the entire distributed infrastructure I had before. Today, if I update one of those things and it fails, I am out of luck. If I updated my home hub the other day and my Nest heating isn't working, it started snowing, I escaped to St. Andrews, I don't know what's going on. These are not fixable by humans, right? Because the entire system has no one kind of operating system running it in order to mediate all these things. And so the good news is that there's a lot of movement to try to consolidate the low-level chips inside these systems. So ARM in particular is being really good. They've got a modern 64-bit ARM called ARM64, AR64 particularly. And you can even start renting on the cloud ARM-based servers. So Packet.net is a particularly good service if anyone is wanting to dip their feet into getting more powerful ARM machines without having just a Raspberry Pi there. And there's hypervisor support for all these things are landing in the relevant repositories inside Mirage, OCaml, Zen, and so on. So the embedded ecosystem is getting to the point where it almost matches the cloud-based ecosystem for x86, which is really encouraging. So all of the primitives we need to assemble these IoT systems are finally in place. Now, it's just a matter of software and a bit of research to figure out exactly what these systems we're going to build look like at the low level. And I know I've been harping about libraries all the time. Hope you're getting a sense that libraries are important. Because now that we're hitting IoT, if we just started doing this from scratch, we'd have no luck. There's just so much momentum you have to build up. But having access to all the libraries from the past, the last 15 years of accruing these kind of components, lets us actually assemble really bespoke, all the way down to metal systems that have just the right levels of isolation and tailoring required for your particular deployment. So it's just like when you're carving the case for one of these physical devices, and you'll have an artisanal desire to make it look as good as possible, the same should extend for our software and hardware as well. So we can use the library hypervisors to pick the minimum amount of support from the software to have hardware virtualization. Library kernels give us the ability to take scheduling logic and all the different pieces, like how do you drive the hardware for the sensors and so on, and apply that just right. And library applications like Mirage OS give us the protocols and the business logic to tie all this together. And then we can combine all these things into one software stack that is just doing the minimum required on IoT. And this process still feels artisanal, still feels like kind of a maker thing, but before you know it, it's just being democratized. And this means that systems online will support this stuff by default. So continuous integration, for example. How many of you, when you're doing your work, have used any continuous integration systems like Jenkins or Travis? So, wow, this is better than Cambridge. This is great. Because I shall have a Travis slide in my next lecture. So Travis is a service that lets you just write a few shell scripts like Docker files and then run them every time you commit to your source code. And traditionally, it works really well for web applications and so on. It means that every time you're committing, it's continuously building and telling you when things are going wrong, and it's running tests and so on in the background. So at this point, IoT just has nothing like this. But by using the same tools that are used on the cloud, like Docker and Kubernetes and VMs and so on, we can bring that discipline over to ARM-based devices, MIPS-based devices, and benefit from that community being moved in here as well. So this is what I mean by when you democratize something, it means anyone can use it. You don't have to be a specialist in that particular area. So how do we program with all these in practice? Because remember, my message hasn't really changed from the first lecture. We want to take these high-level languages and empower you to build systems using those. So Rust and Go and OCaml and things like that. So how do we actually use these in practice? The big problem is the sheer number of combinations. Every single ARM device at one point just had a slight quirk. It had some routing difference in the hardware, or a different wireless controller, or a custom boot layer that the low-cost manufacturer put in. And there's just no way to keep track of all of these different combinations. And then to make it worse, sometimes you don't know how much, even if you have any storage available, because you might have a tiny chip with 1 megabyte of flash that you need to manage, and so you don't want to have all the overheads of managing external storage and that kind of stuff. So is there some way we can express these combinations in a principled fashion that you can reuse that tell you and expose the infrastructure of it to the end user? Of course, I don't deal in rhetorical questions because I have the answer straight away. And the answer is called Factorial. And what Factorial did was, when we started developing Mirage, initially it only worked in the Xen hypervisor and Unix. And then rapidly the community started coming in and contributing tons and tons of new interesting hardware targets. So IBM came along, Dan Rosemond, Ricardo Kohler, and Martin Lucena, and they created a new hypervisor based on library hypervisors and called Solo 5, and they contributed that to Mirage. And then someone else added KVM support, and then Facebook came along and they wanted JavaScript. So a random fact about OCaml is that Messenger.com is 80% written in OCaml and compiled to JavaScript live on the website you use. And the native apps are also being rewritten in a variant of OCaml called ReasonML. So they've come along and they want to take some of these libraries and have their app-based development and JavaScript development interfaces. So then we had to internalize that as well. So the Mirage application became a very complicated mess of if this happens and you have to do all these different pieces. So what we did was, they said, well, let's calm down and break the problem up. And we designed a domain space language called Factorial that lets you describe the shape of your unikernels, that describes the things that they need, and then you can group those things into, those types into groups, and then you can generate code that will go off and do a search and figure out what a concrete implementation of those types are, and while respecting all the constraints, will assemble a unikernel for you. And so this starts to look a lot like the concept of device drivers, where the operating system hides what the hardware does and gives you kind of grouped high-level abstractions. Except that, and this is actually why Mirage is named what it is, because it's just a series of definitions and conventions you have to obey, and then it disappears behind all the implementations of the libraries that are just normal OCaml code. And so if we can use Factorial to assemble these unikernels and describe lots and lots of different ways of building and putting them together, and do that in a structured way, then we have an incredibly powerful system to scale to IoT, because it will let us tailor just the piece you need for a particular device without rewriting everything else as well. So let me just dive in and show you what this looks like to build a website, for example, one that runs the Mirage website at the moment. So we're going to start off with a little bit of code. Now, if you remember, I had a module called main in the previous version, and what that did was it defines this module main, and we have a little hello world here that's sleeping. And what is happening is that this module main requires a console, and the console is how you just talk to the outside world. I remember I showed you the console from their live website earlier. And then some time, so it has a notion of time. And it knows nothing else about it. Then using only the these things here is this device drivers. This code is running. It's using the console to log. It's using the time, and it's using our cooperative threading library to sleep until the logging is completed. Then it sleeps for a second. Then it prints world, and then it loops. And here what it's doing is that it's looping for a fixed number of times. So it's looping 4 times, and then it's stopping and just returning nothing after that. So to make this work, we define the shape of the job, which says that my job is a unikernel called unikernel.main, and it requires a console, a time, and it results in a job. And this domain-specific language lets us build up this description, and then I can register a real instantiation of that, which says, please just give this a default console because I just want this to go to the Mirage's console, and give it a default notion of time. These are just defaults you can fill in, but you can fill in bespoke time sources afterwards as well. And then you can say to Mirage, well, given this configuration, could you just describe to me what is going on? What is my unikernel? And so by describing it, this is putting in the dot format. This is telling us, well, we're starting with Mirage, and this is the main entry function for your unikernel. And then what I also need with these dotted lines, I need a key from the environment to tell me what the arguments were from Unix. And then I'm going to supply you with a console module and a time module. And then there's also a logging system as well in the background to do this. So it's basically giving me the structure of my system. And then I can write my logic so that it depends on, for example, an environment from something I pass in the command line for Unix. And that's everything it needs. Then I'm just recompiling it to run as a Zen unikernel, so it doesn't require any Unix. I want to completely ditch Unix from this entirely. Now the description has been specialized differently so that it depends on the Zen kind of boot system to give it its command line information, because there is no command line in Zen. You're just booting a virtual machine. And then it uses the Zen console and the Zen notion of time, and it's linked in all of the right kind of Zen libraries to make that work. This is just our hello world. So it's just showing us how 2 different instantiations might be fitted together. Then what Mirage does is that it actually turns it into a real executable. So it generates a code for Zen to say, given I had all of these abstract notions of time and consoles, I'm going to find a concrete version for the hardware that you've chosen, and I'm going to generate the code to actually instantiate and boot this backend. So in the case of Zen, it's applying the module, our abstract module from, known as a functor, from our fragment of logic. And then it's taking the Zen console library and the time library from Zen, and it's constructing a module where all of these have been resolved into an executable thing. Doing the same thing for logs. It's saying that here's a source of time. And then it's generating the main function, which says basically the boot layer, which says, first of all, force these variables. They're lazy variables, so make sure they're real, and then just run the main code. So this is when you boot a Mirage program, it's just running this immediately. So what's happened here is the user has never had to figure out all of these kind of complex assemblies of things. We've just said, just give me some time, give me a console, and then compile it for Zen, and then it's all generated for you automatically through Factorial. And you just have to type in make. So Factorial gets more elaborate. You can also give it this notion of keys, so you can start configuring different parts of the stack, so that you can say that I want to, for example, have different device drivers, and I want to give my website a title, so I want to supply the title when I configure the unikernel. So in the Mirage thing, you want to lift all of the configuration in the different libraries into Factorial, so that you can configure your unikernel in one place. Some of the keys might be supplied by other devices, some might be supplied by the environment, but they're all put into one place so you can keep an eye on what's going on. And critically, the keys can be supplied either at build time or at execution time if that works in the environment. So you can be developing it locally without supplying all the keys and just having it being discovered on your Mac using Docker. But then you say, I want to compile this for my pacemaker running some IoT thing. And so at this point, you can supply it at build time, and then Factorial will resolve those keys and do even more specialization and compilation. And so the more that is supplied at build time, the more information that we're supplying to our infrastructure to specialize it even more and more. And so the better the application gets. But the cost is flexibility, because you're giving up that particular variable. Once I give my website a name, I can't, for example, vary it by time. I can't kind of give it those kind of little things. So let's see how this looks like for disks. Disks are particularly tricky, just managing storage. Because think about the sheer number of ways that you have to store data on a computer. So if we just wanted to implement a key value store, well, I could crunch the files directly into the binary, so I don't need to have an external file system. Because let's say I have a small image or whatever, or the Mirage website, mirage.io. So in this one, it doesn't have an external file system. We've just taken all the images, and we've linked them directly as OCaml code, and we just serve them directly from the language. It's very, very simple, but it is memory intensive. Sometimes you might just want to say, I'm running on my Mac, so I just want to use the file system from my Mac. So just pass it through. Sometimes you might want to say, I just want to construct a key value store from some other file system, but I'm not going to tell you what that is yet, because I don't know what it is yet. And other times you might want to say, just construct like a tape, a tar archive, and just stream it directly from a low-level block device. So no file system is involved. All you can see is sectors and blocks so you can read and write, so a very low-level kind of device. These are all valid ways to build file systems. And unfortunately, like right now, it's always a dynamic selection if you do this on Linux. There's various device drivers, but you can never specialize it more and more and more. In Mirage, we've now registered a key value store, a generic key value store that's read-only, called T. And we said, just given nothing but a key value store and a job, register that and describe what it is. So this one, you can see our graph is getting a little bit more exotic, right? So we now have Mirage, we now have the Unikernel domain. But what it's saying is that because we haven't given it very much information on the command line, if kvro is set to, for example, crunch, then implement this path. But if it requires a file system, then supply a file system and a block device. If you need a tar archive, then just supply a block device with the logic to tar it. And each of these things represents a different path of complexity that will only be pulled in if you supply that particular key. Now, because we haven't supplied anything by default, all of them will be pulled in and made as options. So you have a big kind of relatively fat binary. But then as soon as you supply that, it'll eliminate things. So each of these options is one of the different types of file system, depending on the value of this key. But we haven't supplied it yet. But then if I just say, what if I say the key value store is now a fat file system? Suddenly the graph just completely collapses, and it becomes much simpler. So if you look at this one, this path down here is now the path that Factorial is taking in order to specialize just the piece you need. So suddenly our binary has been specialized so that only the one file system path has been taken, but I haven't had to rewrite any of the rest of it. And then this is built using a particular way in Unix, using mmap, so you can memory map the system into the Unikernel. Then let's look at the Zen Backend. So we want to get rid of Unix entirely. At this point, we still have a choice here, but notice one of the choices is missing. The choice is missing is the Unix one, because the concept of passing through a file system to the underlying Unix file system does not exist in Zen. There is no operating system, there is no Unix. Just get rid of the option entirely. And the existence of those kind of little dependencies, for example, let's say you want to read just a config file or the time of day or something, the local time value, then you need to pull in a whole file system and you need to initialize it. These are all drags that pull in millions of lines of code. But here what we said was, if you have a file system, it's already available, and you choose to use it, then you can use it. But if not, we have many other options to give you the same path by assembling just the right bit of infrastructure you need. And the Zen backend, because we've told it don't ever depend on Unix again, knows to eliminate those options. And then you can say, here's tar, here's mmap, and here's crunch, but we don't need any of the other bits and pieces. So the critical thing is, built into our little domain-specific language is the notion of what can be included and excluded based on the specialization of keys. So at this point, we want to describe the whole thing. So earlier, I said -t Unix or -t Zen. And you can start to see the richness of all the different backends that are supplied in Mirage by default. So here, for example, if I have a key value store, if it's cubes, which is a very secure Linux distribution, if it's running in cubes, and the idea is it's a desktop distribution that runs every browser tab inside a different virtual machine, then you've got one option for doing storage there using their specific protocols. You might be using different things like Solo 5, which is a different hypervisor, Unix or Zen. So you can start to see all of the complexities of the backends being exposed. So, and these have all been added. When I generated this graph, I had not actually seen the cubes backend before. Someone else, Mindy Preston and Thomas Leonard, contributed that, added it to Mirage, I updated, and suddenly in my own applications, I've got the ability to target these new things. It's a pretty powerful setup because they can extend Factorial in their own directions. And so now people can extend it to ARM and other devices and so on. So some of these options are constrained based on the build target. So it doesn't make sense to do, for example, an x86 specific bit of vector processing on ARM. So it'll simply exclude those, or in this case, based on the OS target. And others can remain dynamic, but it'll have to pull in all of the dependencies to support those. And dynamic is the default that we have in systems today. So if you just build it like a dynamic executable, it's just like you're building a normal application. But if you choose to specialize it, then you can just chip away at those dependencies, and you can use the fact that Factorial will expose its graph, so it'll guide you in the path. And it's also a cool way to discover new possibilities for system construction that other people have built as well. So it's like an exploration process. But it gets even more complicated, right? We've only really looked at disks, and any real system has a tremendous array of peripherals. So networking is really complicated because there's so many ways to configure all the different keys and so on that go into one of these stacks. So, and it's a combination of networking and storage that make Factorial shine. You realize as soon as you put two things together that are complicated, the fact that you can compose these things makes this entire approach viable. It's really easy to show an example with just one thing, convince yourself, and then you try to deploy it for your own website, and it's impossible to kind of use other people's work. So Factorial is compositional. Now, is everyone here familiar with TCP/IP and the way it works? How many of you have done a networking course on TCP/IP? Okay, excellent. Okay, that's good. Explaining TCP/IP would take longer than this seminar. But what we have here is a website written in Mirage now. So we're starting to get more complicated bits of OCaml code. In this one, we have a module main that depends on what's known as a conduit. And a conduit is an abstracted network channel. Because when you write one of these unikernels, you don't know what's going to be at the other end. It might be a wireless connection. It might be TCP/IP. It might just be shared memory to a different virtual machine on the same host. You don't know. You don't care. To serve HTTP, I just want a conduit. And then I will construct my logs infrastructure. And then I will construct my HTTP server using the module system in OCaml based on the conduit. And then I'll simply say, I'll give it a callback, just like you would in a normal callback, to say, let me look at the URI that you've typed into your browser. I'll log the request using my logging infrastructure. I'll respond with hello Mirage world. But of course, you can have far more complex logic in there for real systems. And then you start listening in the conduit in this case on TCP port 80, and then the unikernel goes off. So we know how to build this thing. And the most obvious way to do this is to build this and to try it on your laptop, right? Because I want to test out my HTTP logic and stuff. I don't want to do kernel development or anything. I just want to build a website. And so I want to construct a normal Unix binary that looks just like I built this in Node.js but except using OCaml, but no real difference. So I can describe this thing, and this is now a unikernel. It's taken a conduit called Conduit Mirage. It's given it a little bit of entropy, so it has a source of randomness, because nothing is implicit here. If I want randomness, I've got to ask for it from the environment. And then it's saying that here's a connection to your Unix network stack. Right. And so this application behaves just like a normal application where it'll open dev random to get entropy. It'll make socket calls. It'll read write. It's a Unix binary. You can develop in it. You can debug it. You can get your beautiful website up and running. But now you want to specialize this to your tiny little Raspberry Pi type device running on an ARM thing. So what you want to do afterwards is you want to recompile it to, say, run in Zen. But the problem here is that when you don't have an operating system, you need to pull in an entire networking stack from Mirage OS. So we now need to discover exactly how to implement all of that stuff the kernel does and make sure we seamlessly link it into this application. And with storage, it's kind of okay. It's a few libraries you can put together. With networking, it's insanely complicated. I think I wrote the first iteration of our terrible network stack. It's now a much better network stack. And it took me just 6 months of understanding TCP/IP and all the bits and pieces, and there's just a lot of complexity in these things. So, but no worries, it has been written now. So how do we put it in, right? And it's all in pure OCaml. There you go, problem solved. So this is the result of just saying Mirage describe minus t zen minus dot. We've got our unikernel there, and then is everyone following? Yeah? Yep, good. So there's a tremendous number of options but if you start looking at this, right, let's just go in a little bit deeper here. You can start to see a shape coming out of this. So for example, think about the layering of your networking infrastructure. If I need DHCP, and if I'm going to a direct stack, which is not a socket-based stack, well, I'll need to have an ICMP system to have pings and so on. I'll need UDP here in order to send UDP packets, obviously. TCP, now if you follow it carefully, requires entropy And TCP has an angle going to PRNG, which is pseudonumber random generator. And then this can be implemented by two things, either a special one called NoCrypto, which uses a very smart random number generator, or one from the standard library. And so you can start to see a shape. The actual underlying structure of our networking stack, the ones you should remember from your networking lectures, is emerging in this Factorial stack. And then what I'm going to do is I'm going to specialize my command line to say, give me direct, turn off DHCP, and you can start to see a much more recognizable thing as we resolve some of the options and some of the externalities that make the stack. So in this case, I want a direct stack. It gives me ICP, UDP, and TCP. I still haven't specified PRNG, so you can give me an option there. And then TCP depends on having a clock so that it can decide when to retransmit and so on. UDP doesn't, so it doesn't have a dependency on mclock. So you can start to see which are the simpler protocols. And you can go even deeper. You can say, my application doesn't even use TCP, it only uses UDP. And you can eliminate that kind of part of the graph as well. So it really lets you kind of slice up and understand what's going on and kind of look inside the sausage factory, if you will, and see and understand exactly what's going into the system. And because you can track all this by this tiny little description up here, you can see the power of just exposing configuration in one of these unikernels. What's happening behind the hood when it generates the code? It has to make it executable. So it's resolving all of those module references that we just abstracted over. It's finding concrete implementations from the OPAM package manager, from our OCaml code, and it's assembling them in the right order to assemble a stack. So this is code that you would have to write by hand if in the old days of Mirage. With Factorial now, you just say, given a series of functors, just go apply them all. And you can see, again, the beautiful kind of layering in our systems with exactly how these modules get applied. Ethernet comes in from a hardware device. ARP, which gives us a mapping to IP addresses and MAC addresses, is made from an Ethernet device, a clock and time, because ARP needs notions of timing out and so on. Then IP is made from ARP and Ethernet. Then UDP is made from IP and randomness, so you can generate the random generators in UDP packets, and the IP address also needs that. And then TCP is much more complex. It's made from IP and time, and lots of all the other pieces. TCP basically splats over everything. And then finally we have a unikernel, which is taking all of these and building one of these up. So you can see the nice structure thing. You never had to write any of this. You just typed in the actual configure command line. And what Factorial does, it exposes all of these keys into the command line as well. So you can see, for example, I've specialized my IP address to be one specific IP address. And I hope you're getting a sense of just the depth of specialization possible here, because not only can you say DHCP or static IP address, but this IP address becomes a constant inside the source code, which is then compiled with the rest of the compiler. So if you structure the code correctly, it means that you can just eliminate a whole bunch of options and dynamic processing, because you just specified as a variable inside your code by generating the IP address exactly what it is. So you can make really, really tiny things. Now, we're not all the way there yet. This doesn't come for free. You have to structure your code so it's amenable to this kind of optimization in functional code. And we're most of the way there, but there's large chunks of code that hasn't worked. So OCaml itself has a very elaborate inlining system called flambda, which essentially, as far as you can tell, it tries to analyze the scope of variables like this and just form data paths through there as well. So with flambda coming to modern versions of OCaml, we're hopeful that we can do incredible specialization with these systems. So just a recap of Factorial, where when we started with OCaml, I kind of gave you some fairly vague promises, right? That functional programming is good and composable and all that kind of stuff. But the module system is one that I encourage you to explore if you're interested, because you can install the OPAM package manager. Just go to opam.ocaml.org, and you can download any one of the small individual libraries, and you can see exactly what it does, both from a signature and from an implementation perspective. So it's a great way to learn the innards of operating systems. And what Factorial does is says, well, if you're working on Unix, here's all the Unix-related libraries. If you're working on Zen, here's all the Zen-related libraries. So I've had students or open source contributors who want to know more about Zen, and I point them at Mirage and say, just go read the OCaml code for the Zen device drivers, and that'll give you more documentation than kind of any Zen documentation, because it literally just implements the code in a relatively high-level fashion. So the feedback that only comes back is we don't speak OCaml, but that is changing now because books have been published and so on, so people are getting the hang of the language. So now as we build up a critical mass, we can see that. And Factorial gives us the ability to build future-proof systems as well, although I'll come back and confirm that in 10 years. But the idea that we can incrementally specialize the graph, so we can expose the innards of the dependencies that are lurking within systems like this, and then turn that into a full unikernel. So by using this in Mirage today, you can all build unikernels and use that the graphing mechanism, the dot mechanism, to see exactly what's going on inside the hood and learn more. And in a real IoT system, to bring this back to IoT, configuration is basically the biggest problem, because you want to have the same application logic, and you want to compile many, many different nodes that are specialized. You might have a Raspberry Pi 2 and a 3, very, very different. With Factorial, you can just build one spec that says, give me binaries for both 2 and 3, and make it all just work. So you can now see how you can start building up these kind of structured graphs of things as we go through. The set of devices is fairly high. Like we have signatures where you can create ones for new domains. You can break this whole operating system cycle of bloat, because in the world that I described when we started, we're always adding layers. In Factorial, we're extending it by adding to the graph. And you can choose how to traverse the graph. You can choose to layer everything and build a fully dynamic system, or you can choose to traverse it in a very focused, narrow path. And so this is how architecturally we fix the state of operating systems, because by adopting this kind of build time discipline, it means that we're no longer ON by the number of years. In 100 years from now, we might have some insanely complicated Factorial-style system with quantum computing and virtual reality or whatever, but fundamentally, it's one that you assemble at build time. And so you're stopping the dynamic layering that is happening in our systems as well. And functional programming is directly useful for showing the world how modularity is useful for this kind of large-scale system construction. I'm under no illusion that the world is going to shift to OCaml anytime soon, but certainly by building a full-scale kind of OS abstraction like this, then we can actually have an experimental vehicle to say, how should we guide other operating system efforts in the same direction, because we are describing operating systems in this structured style. I hope you saw that from the TCP/IP description, because normally in an operating system you have no idea what's going on, right? With this, it naturally flows out of the compositional definition of the network structures. And to give you a sense of where we're going with this, we're building new things for abstracting remote and local communication as well. So sometimes you're just operating on an IoT devices right next door. Sometimes it's happening remotely. Dealing with key management, very, very hard to authenticate users and to deal with all the complexity therein. And even things like data science, where sometimes you want to try a little machine learning algorithm on your local machine and then deploy it to use custom hardware like FPGAs and so on. And so for that, Factorial is the perfect place to kind of group some of these bits of logic together to say, I don't have access to FPGA hardware accelerators here on my Mac, but I will over there. But here is a software version to let me develop it, and then stage it off into that part of the world. The programming language name for this is called staged metaprogramming. So in OCaml, we have Jeremy Yallop and Leo White who are experts at this. And the idea is that you're basically running code that generates more code, that generates more code. It's getting simpler and simpler and simpler. So this technique is a wonderful technique. Factorial is just one part of the spectrum of staged metaprogramming, where there's systems such as MetaCaml. I remember Idris, Edwin is finally here now, where you can do partial evaluation based on variables being put in. So languages support metaprogramming to different levels. But the idea in OCaml is that by adding staging, you can generate code that sheds complexity and tries to eventually, hopefully, not even require the OCaml runtime. So you can run on tiny 8-bit microcontrollers that are essentially can only support C code now, but you've built it from a high-level OCaml description, which means you can check safety properties and a whole bunch of things of that nature. So how does this even work? Like, how would you put one of these things together? Some of the research questions we're asking right now is, take this lecture theater. You can imagine the walls being blanketed with thousands of ARM processors. Your chairs having sensors in there for pressure sensing. If you're falling asleep, little shock actuators to wake you up, or shocks to me because it's my fault. This kind of stuff will just happen. And the basic problem is we don't have an operating system that works. So show me pictures of cute puppies. Sorry, in stressful situations, I just got to sometimes look at a puppy. Just give me a second. These watches suck. They never work. The problem is, all of these things, what they're doing is going all the way to the internet, is going to apple.com, it's trying to parse my voice, it's trying to connect to EduRoam, And this is not a sustainable operating system for the future of trillions of devices running in our buildings, right? You want the building to run and operate locally without any kind of external connectivity and have it just work. And so what we're trying to figure out is what is the role of an operating system when you're saying that it's actually managing not a computer, but a distributed collection of hardware with lots of heterogeneous endpoints. So things like little ARM devices, watches, and as you enter the building, it can authenticate you, it can keep track of where you are, and then give you very, very low latency, 10 millisecond access to the world. So it should be a bit more like Star Trek, where if you think about Star Trek, the first thing you think about is not Internet of Things, right? Like normally it's, it's Picard is when it's going engage or this, and then the environment reacts immediately. And that is what an operating system is, something that should just fade out of the way and provide services for you to actually do your job. So things like voice recognition or gesture recognition and encryption and all of the things you need to do in a physical space, those can still be supplied by operating systems. They will still do the core bits of functionality that you need from an operating system. They will isolate my encrypted data from yours, but they will still let us work together in the same kind of physical space. And so things like unikernels and Mirage, these are all technologies that are helping us construct this kind of new operating system. What the author of, the original father of ML, Robin Milner, later in his life worked on something called bigraphs. And this is a calculus designed to solve exactly this kind of problem where you can have containment relationships inside by having DAGs multiplied with trees. But the idea behind bigraphs is a way to express the mathematics of physical spaces and tie them into programming languages. So it is interesting that we're coming full circle by looking at how to apply Mirage to physical spaces. And it's basically this latter half of Robin Milner's incredible legacy after he left Edinburgh. And I'm not going to do the details, but if anyone is interested afterwards, we've actually got architecture, and we're putting some of these spaces together. You'll be glad to know that it uses blockchain technology as well, using a little database called Urban. So everything is tracked and stored, but it also has secure deletion and the ability to encrypt and to track you across physical spaces. So I can send anyone who's interested in that a paper. And the basic design considerations are, what should you do? Should you change your behavior in order to support this new world of unikernels? Well, there's just a few design considerations to think about, which is, don't build big monoliths. Try to figure out, can you just build something as a library? If there's one word you take away from this, think of library. And you try to break out your logic in such a way that you're not imposing a policy in the way that people use your code. And open source that library as well, so other people can try to use it. Doesn't matter what language, anything, it builds up the overall kind of ecosystem of this world. Try not to reinvent some technologies like RPCs and communication. It's very common to build your own system here. There's some really good off-the-shelf things like Google's Protobuf, for example, in gRPC. Captain Proto is an incredibly good one where you can do cross-language efficient RPCs. And so by abstracting the way that you communicate, you make it much easier to build a unikernel because you're not tying this specific mechanism of communication into your logic. And I showed you these CLI interfaces. These are all like drivers. Try to, instead of having lots of configuration files and so on, try to lift all your parameters in a way that they can be put into one place so that you can manage the complexity of these systems much, much more easily. So in high-level languages, like functional languages like Haskell or Idris or OCaml, it tends to be easy to build extensible CLI interfaces and to have little terms that fly around and add kind of command line options and so on. So use those to abstract the logic, yet still make it configurable by your user. And in this way, you can avoid the big kind of monolithic design space. So the Unikernel movement is basically how do we make all the things as libraries, more boot libraries, more scheduler libraries, more logging libraries, more protocol libraries, more device driver libraries, and keep that kind of mass going up so it's changing the way the systems work. I've talked about my own work in some of this space along with my colleagues, but there's an entire ecosystem of people doing these across big companies and hack spaces and such as well. And so I just wanted to give you a taste of just a few projects you can contribute to if you're interested. This is also just a wonderful way to learn about systems programming as well, because you're not stuck with 20, 30 years of other people's operating system code. In these cases, these are young, dynamic projects that are often just full of bugs and stuff, but they're vibrant and they're trying to kind of break new ground with thinking about operating systems. So there's maybe over 50 unikernel projects that I've spotted around the web now. A lot of them on unikernel.org. Some of the bigger ones are Solo 5. One called Unicore, which is an exciting way to build a Linux-style build process to C-based applications in Zen. And then we have library operating systems like the ROM kernel as part of NetBSD. Linux has been converted into a series of libraries already. LinuxKit is one that I used to work on with Docker. And of course, things like the library long times. If you like C++, there's include.os is a really good option. Haskell has HalVM. Mirage OS has obviously there. And also big complicated storage systems. If you like Git and version control, look at Ermin, which is the basis of the blockchain technology I mentioned as well. And this lets you abstract your storage in such a way that you can track all of the changes and just git clone your infrastructure as well. So this has led to some really interesting spin-offs in this space. But overall, though, while the systems world sometimes just seems that it doesn't really change that much, right? It feels we're always just porting the systems, making graphs and so on. But this move from monolithic kernels in the last 10 years into standalone libraries is quietly transforming the systems world. I hope I've given you a sense of some of the applications for this, by the opportunity for programming languages, the opportunity for verification eventually, the opportunity to change the way that we think about the hardware-software interface. But then also the adoption by big companies, so Microsoft's shifting seats, so companies like Docker embedding unikernels in different parts of their stack. So this transformation is happening because as the sea change rises, the opportunities to use these in lots of different contexts is increasing, and we'll see more and more of these things as well. And so in a few years, it'll turn into just the default way. You're wondering why you didn't use these in the default way to build big complicated systems, or at least I hope so. This series is a result, as I said, of a huge amount of collaborative work with my colleagues. I'd like to thank them again for providing with just so much incredible material to talk about. I've worked with them in many, many different contexts in open source code. And I really hope to see some of you among these names as well in the future. So get involved by going to the websites. And if you don't understand anything, you're always welcome to drop. Most websites have a contributing file where you can ask questions and so on, and they give you pointers. But if not, you can always just drop me an email, and I'll do my very best to try to answer and try to convince you to come down to Cambridge to join our master's and PhD programs to do more work in this space. But also, when you're out in the world, just remember, keep your minds open for opportunities to take some of these technologies and to solve real problems that you'll face when you graduate and go out there. And so this is how we're going to make the world a safer and better place to work with. And hopefully, our smart lights and so on in a few years will be instantaneous. When I find my watch again, it'll be one that works and shows me puppies when I need it. And this is work that I hope that all of you will work on to improve the state of our cyber physical infrastructure. So thank you very much for your time, and I'll take any questions you have now.
Any final questions?
Where's the pub? I'll put my slides online. So there's a lot of information here. There's no need to ask questions now. But if you have any questions, you can drop me an email to anil@recall.org.
Surely. There's one, yeah.
There we go. Hello.
Is that the prop wife?
I'm sorry?
Is that the prop wife?
Oh,
We'll find your watch.
do you know what yeah, I'm not sure what that. You know what I forgot? The new port. Let me show this very quickly. The latest port I mentioned in Mirage OS was done over Christmas time by one of our colleagues, Sadiq Jafar. And can you see this? So it's this device here. So I'll just pass it around. Just Tristan, pass that one around. So this is how small these things are getting. It's got Wi-Fi. It's got Bluetooth. It costs $1, and it's got a megabyte of RAM. And all you can do is you can run OCaml code on it now. And we're currently in the process of hooking in the TCP/IP stack. It uses a new CPU called the ESP32, which is a custom 30-bit microcontroller. And so we're adding in native code support into OCaml and so on to pull that off. These things run on batteries. They're absolutely tiny. So I've just ordered 200 of them. I don't know what we're going to do with it yet, but we're going to something involving a building, I think. So cheap. So the future is happening very fast with these things as well. So Mirage is going tiny as well. I was hoping to give you a demonstration, but I lost all the cables on the way up here because of an incident with a Tesla. But the blog and so on, and the Mirage blog has all the details about that as well. So yeah, I can pass it around and show it to you, but you get the sense of it just being a tiny, tiny little device that runs on batteries. So I don't need my watch. I'll just use one of these.
Yep.
So how would having the operating system libraries help your Apple Watch to answer your questions?
It's a great question. So the question is, how would having the operating system libraries help you out to answer questions? There's problems across the stack here, right? So whenever you're trying to build these local answering systems, you need to have a lot of machine learning happening locally. So you want to do things like, as you walk into the building, you want to download the details of your voice and so on into the system. But if you only have 10 milliseconds to respond to something, so the 10 milliseconds is, ask me a question. Anil? I mean, it's just a few, Anil, just our social cues are very sensitive to latency. It's called the uncanny valley, where you feel like you're losing the illusion of interacting with a real person. So to do that from a computer system, there's basically no time to do anything you've got to almost predict what's happening. So in our system, we actually have plenty of time, right? When you come in here, I've walked into the building, I could have authenticated when I walked into the door. There, by the time I come down here, I spend minutes preparing and setting up. So why did I need to do anything here, like plugging in computers and stuff? I should have just been able to get my data seamlessly downloaded into a computer that was already sitting here, encrypted with the local computers. So where the operating system libraries help you is you can split up the order in which you do work very easily. So rather than saying that as soon as I connect to my watch, the OS in the watch is activating and is doing all of the things it needs to do on the network, that work has incrementally been done as I walk through the building in an encrypted way. So the OS libraries let me break up that work and run it all over the place. And it's completely different, non-conventional things. So the watch might have known that I love puppies, and then it would have had some puppies encrypted and stored to the building processors when I walked in, because humans are predictable. And then by the time I asked, the actual logic to serve the request would be running on a screen here or on a watch here. So the watch would not need to have all of the logic that it has on it right now. You wouldn't need internet connection. So it requires re-architecting the way that we do machine learning and service discovery. And that's where these OS libraries come in useful, because they let you kind of turn things 90 degrees very easily. They don't solve the problem by themselves. They just make it much easier to solve.
But I still don't understand how library systems would have that happen compared to just like one big.
So when you have one big system, it tends to be all mixed together. So things like the policy for how to do things. So the interface, for example, to a TCP/IP stack is open a connection, and then the stack goes off and sends all the packets back and forth, and then it gives you back a connection, and then you can use that. But if you want to do this in a different way, with a library structure, what happens is that you make the function calls into the stack, and then you decide how to drive the library. So the library tends not to just run itself. So this means that if you wanted to just stop with the connection after sending one packet, then go do something else, and then come back, it becomes much, much easier to do that. So all the library structure is saying is that if you have a big, complicated, intertwined system, we will have discipline in how we structure our code, so that if you want to have a very different way of running the stack, you just override that part of the library. With a big system like Linux, for example, you have to fix the whole thing. You tend not to be able to just go in and make a targeted kind of attack on one of the pieces. So it's more of a discipline around how you can change things. So if you want to radically prototype something that is like a building where bits of the code is running in lots of different places, you could do this with Linux. It just takes a lot of time, because you have to tease apart all of all the policies, the schedulers, the device drivers, and so on. And you almost have to fight the system before it'll do what you need it to do. With library operating systems, you just grab the pieces you need. By default, there's nothing. So you know exactly what's running at any given time. So you can then see exactly what the system is doing. The difference between starting with 25 million lines of code and starting with 0 and building your way up as opposed to working top down.
I think we had one final question here, was it?
So, yeah. So I have a final one, but the port to the ESP32 or the extender architecture, did you write another backend for the OCaml compiler, or are you generating C code which is then compiled using the extender BCD?
So it's in between. So OCaml has multiple backends. It's got a bytecode backend where it's a portable bytecode that it interprets using a C interpreter. So we don't generate C code because you can't, well, it's difficult to generate C code that expresses the stack layout of a functional language like OCaml. Exceptions and stuff become hard. But the bytecode is very portable. You just have to compile a small single C file and it runs in there. So this thing here is running using bytecode. And we have an intern coming from France in a few weeks to build the OCaml native code backend. And that looks very straightforward. ESP32 is interesting because it has a whole bunch of extensible instructions for things like zero-cost loops and stuff. So those, you go to a Chinese website, you click a few boxes, and you can get a chip synthesizer exactly what you want. So I'm just going to go to the website and click on it tomorrow and see what I can get. I love this idea that you can just customize and get delivered to you 1,000 chips with exactly what you need. It's very Unikernel-like, in fact, as well. So we're writing a new backend, but it'll be interesting to see how we deal with the extensibility of the ESP32. We haven't done that before in OCaml. I do need that ESP32 back, by the way. I've only got one. Excellent. Excellent. Thank you. Safe hands, I think, up there. You're running away.
Any final? Yes.
Having nicely reduced everything to just what you need, do you then make a nicely well-defined attack surface for evildoers?
Oh, that's a good question. So, okay. So the question was, if everyone heard it, by reducing everything to this minimal thing, are you just providing people with a focused attack surface? The answer is yes, and I think it's very much the right thing to do, because any determined attacker can basically remove any externalities they don't care about and just aim for the weak spot of the system. So we're eliminating possible weak spots. We're not claiming to build a super strong spot, but we're getting rid of a whole bunch of other things that could be weak. And we're focusing our efforts on the strong spot to make it stronger by writing things in OCaml and so on to focus it there. But by no means is it immune to attack. So we think it's better. Things like the Pinata, the Bitcoin Pinata, they don't show it's secure, but they show that it's not amazingly insecure. $180,000 is worth someone's time to break into. But security by obscurity, which is you just sort of hide your weak spots, it doesn't work in the wild, because anything of value, people will spend the time to work through the obscurity. But it's a great question. You have to think through what properties we're thinking about for the bits that are remaining. And they're getting stronger and stronger, but by no means like fully immune to attack yet.
Would you be able to use something like Factorial to design some like very modular containers? So like have it so that you expose it like something like a libc, but maybe and then just plug in whatever pieces you need to like create your own specialized container.
You can absolutely do that, yeah. So we've actually got Docker and Mirage integration, so you can build that today. The only thing that means is that you basically build a file system with the data that you need inside it, and then you go off and do that. You can use Factorial for non-operating system things. So one of my collaborators, Liang Wang, has a system called OWL, which is a data science platform where you can build quite complicated functor stacks of algebraic differentiation and all the different algorithms you need in machine learning. And to select those is quite a complicated process as well. So he's starting to write Factorial abstractions to assemble functor stacks of a distributed machine learning system versus a local one with symbolic processing and one with stochastic kind of data and so on. So all these different options. So anything where there's a lot of configuration and a lot of options, or even a few, you just apply to everything, Factorial works there as well. Just anything you can express in OCaml. So.
Okay, I think we've exhausted the questions.
Thank you. You have been the greatest audience. I didn't see anyone asleep this entire time. I was the only one. So thank you so much again for your time.